A very nice afternoon to everybody, ladies and gentlemen. Welcome to the session about OSPF LSA types made simple. My name's Peter. I am currently with Cisco Training Bootcamps team, so I live off of trainings. I do hope, though, that this session here is not going to be too boring and too bookish. I have to say, though, that OSPF LSA types, as you probably all know, who try to work with OSPF, or try to troubleshoot OSPF, or even learn it for certification purposes, you know they bash them over your head, and they give you those lists, and then you wonder, why are there so many? And what do they do? My goal is to try to explain why they make sense, the way they're invented. I cannot simplify them too much, but if you understand why they're useful, that's what it makes all of click. I call this session also known as OSPF is a jigsaw puzzle freak, because that's exactly what's happening. By the way, anybody here likes to put jigsaw puzzles together? Some of you do. So imagine something like this. A simple topology of 3 routers. Imagine now that this was a picture we were supposed to put together from a couple of jigsaw puzzle pieces. So it could look like this. One jigsaw puzzle would be there for this R1 in the diagram. Another jigsaw puzzle of the same type would be there for the second router, and yet another one would be there for the third router. This is how OSPF sees the world around itself. Every network object is a jigsaw puzzle. And, as it turns out, different types of network objects are different types of the puzzle pieces. What if I had this type of network? So, just 2 routers, a switch in the middle. Well, what OSPF often does here is say, one of the routers is going to be one jigsaw puzzle, fair. The other router is going to be a second jigsaw puzzle, also fair. And imagine that the network itself might be a jigsaw puzzle on its own, and I'll explain later why that's a good idea. All in all, when we talk about the link state advertisements, this is what they do. They put together a map of the network. To OSPF, they're the lifeblood, they're the knowledge, they're the conscience. Because OSPF really doesn't care about addresses. Did you know that? OSPF doesn't care about IP networks. OSPF cares about topology. It wants to know precisely. And so that it can know, it needs to know precisely what the routers are and what their interfaces connect to. It's a freak about detail and a freak about topology. It wants to create this mind map inside its memory so that it knows precisely how the network looks like. And that's why it pieces together the understanding of the network's topology from these jigsaw pieces, the LSAs of different types. And we have a jigsaw puzzle type that represents a single router and its immediate neighborship. We have a jigsaw puzzle that represents a multi-access network that connects 2 and more routers together. We have a jigsaw puzzle that represents a prefix somewhere else in another area, but still internal to our domain. We have a jigsaw puzzle that represents possibly an AS, autonomous system boundary router, that connects the whole domain to an external world. And we have a jigsaw puzzle that represents the networks behind that router that connects us to the external world. Notice how the scope grows. A router, a network between routers, prefixes from other areas, our border connections to the outer world, and whatever is outside behind those connections. That's what the LSAs do, and this is why they are also sorted in this way, because these are precisely type 1 to type 5. So let's go and check what they do. The first type is router LSA, or LSA type 1, who originated every router for itself. The LSA describes someone. Whom does it describe? The router itself. It may sound a little redundant, but we will have LSAs that are originated by a router but describing somebody else on its behalf. And what does this router LSA contain? Information what this specific router is connected to. All right? So, let's check a topology. Let's assume I have these two routers and this zigzag connection is a point-to-point link like the old serial ones we used to use 15 years ago. Okay? My question is, how many LSA types 1 would be in OSPF running here? 1, 2? Remember, each router generates one for itself. So it would be 2 here, 1 for R1, the other one for R2. What would R1 say about itself? I can hear router 2, I'm connected to it, so I will point to router 2. That's what we do in that LSA 1 over router 1. And what does router 2 do? I can hear router 1, so I will point back to the guy. Notice that we have those arrows, they have their direction. We always need to follow the direction. And this is also why they are independent, why we can have also, it's not a good idea, but we can have different link costs from each side. They would be reflected on those individual arrows depending on the direction. What about here? How many router LSA type, well, LSA type 1s, router LSAs would be present here in this topology? 3, perfect. 1 for each router. And what would they say? Well, router 1 is only connected to router 2, so there would be just a single pointer, single link. Router 2 in the middle connects to both the guys, so it would point to each other, like this. And router 3 would point back because it's connected only to router 2. Notice that when you follow those arrows, you can get from anywhere to anywhere else. This is important. And what about this? So, how many LSA type 1s? 3 again, nothing new. And they would each point to each other. 1 points to 2 and 3 because they are connected. 2 points to 1 and 3 because they are connected. And 3 points to 1 and 2 because they are connected. In fact, it would seem that with these router LSAs type 1s, you can describe any arbitrary topology. Technically you can, not always efficiently, but you can. We can do something more efficiently with the second type of LSA we call the network LSA. And if you don't mind, let's take this as a, for comprehensive purposes, but let me go to a diagram. It's gonna be more simple to explain why we need this network LSA type 2. Imagine I have a network that looks like this, 4 routers on a common network. If I wanted to use the previous approach, how would the mental model of OSPF, of this network look like? So always, first question, how many router LSAs would be here? I have 4 routers. So 4 LSA type 1s. And what was the previous approach? If I can hear the other router, I will point to it. So here everybody can hear everybody other, right? So 1 would point to 2, 3, and 4. 2 would point to 1, 3, and 4. And so on, and so on. And the model would be workable, but quite dense if you think about it. And there are algorithms that need to visit what we call the node and check every single neighbor, what happens there if I can find a cheaper route. Well, this is a densely populated node, and it takes memory, and it takes CPU space. However, this represents the connectivity as it truly is. And that's why this is also what we use on the OSPF point-to multi-point network type. You remember those hub and spoke frame relay stuff that we used to do. This is precisely the ideal mode of operation because I won't assume a connectivity. I need to hear from the guy, and then and only then I will put that connection there. But this is a little pessimistic approach. Well, what if I could create a mental model of the network as it truly is? And what is the true model of the network? 4 routers with a common segment between them. So let's try to do that. I will need those 4 router LSAs because they are about routers. But I need another piece of puzzle that says I am a network. Essentially, I'm quite stupid because I'm just a cable, but I'm connecting all of you together. And this is the LSA type 2, the network LSA. And what do we do now with those links? Well, every router is connected to the network, so the router LSA will point to that type 2 LSA. And the network will say, I am connected to all of you guys. And again, if you follow the direction of the arrows, you can get from a router into a network and to any other router. So again, it's fully connected. But wireless, the top approach needed 4 times 3, 12 links. Here down, you have 8. So it's not as computationally complex and not expensive. This is the network type LSA. It represents a multi-access segment because it allows us to create a simpler mental model of the whole network. And who generates the LSA type 2? The designated router. That's why we elect it. It's the designated router that is responsible to speak on behalf of a multi-access segment in the link state topology. By the way, would it make any difference if there was another switch here and those 4 routers have been somehow split between those 2 switches? Would it make a difference? To this network model, no, because all I care that in the middle is a shared medium that connects us all together. That's why. And now the combination of all the router LSA and the network LSA allows us to precisely and efficiently create a mental model of any topology inside a single area. And that's what we do. So, without talking probably too long here, this is what we would do. 4 router LSAs because I have 4 routers. 1 network LSA because I have 1 multi-access network here. And the links, well, router 1 is connected only to the network and to nobody else. So there you go. The same for router 2. Router 3 is connected to that network and also to router 4. And router 4 is connected back to router 3. And this would be the model of this network. And once again, this is all you need to represent any kind of routed topology inside a single area. You don't need any other LSAs. Yeah, of course, the network also has to say that it connects back. One comment now that we're on this. What do you think would happen here if I did what we do today? 3 routers, but Ethernet connections. Yes, physically they're just crossover cables or fiber. They are point-to-point, but they are Ethernet. What's going to happen? What do you think is going to happen by default in OSPF? Type 2, yes. Let me show you. This is the point prototype. OSPF knows that Ethernet can be a multi-access network technology. Yes, there is only a single router, but where's the guarantee there is not going to be another one? So there will be 3 or 4 on the same segment. Therefore, by default, it works on this multi-access network type, and it complicates the network model as is shown on the bottom topology, because for both of those networks there, it creates this network LSA. By the way, IS calls it the pseudonode, and it's precisely the same thing. Precisely the same thing. And the mental model of that network would look like this. Is it simpler than the top topology? No, not really. Here is OSPF getting a little over-engineered. This is why It's actually advantageous if you know that you have physical point-to-point connections between routers. Also configure them as IP OSPF network point-to-point. You don't lose 40 seconds on DR-BDR elections, and you don't necessarily create those network LSAs that, in this case, don't simplify anything. All right. Let's move on. The third type of an LSA is called summary LSA. Now, this LSA is there to represent an IP prefix that exists in a different area than myself. Who originates it? The area border router that connects to that other area. And what does it contain? The information about the prefix, so the subnet address, the mask, and the distance or the cost from the originating ABR. So let's have a look. Let this be our topology. We have area 0 consisting of just 3 routers connected with a common switch. And we have area 1 that contains essentially 4 routers, 3, 4, 5, and 6, with point-to-point connections. And now remember, every area keeps its own independent link state database. Every area sees the whole network differently. It sees itself in detail, and whatever is outside, it's a little cloudy. So let's see what the routers in area 0 see. I'm talking about area 0 now. So again, my question, how many router LSAs in area 0? 3, because there are 3 routers. How many network LSAs in area 0? I'd say 1, because there's 1 such network. Okay, there we go. Let's have them connected the way they should be. Perfect. However, router 3 is also an ABR between the 2 areas, and it knows that there are additional networks X, Y, Z, and Q somewhere in area 1. We have implemented areas because we don't want to see the topology of the other one, but we still want to be able to route there. So while I don't want to carry over topological detail, I want to carry reachability information. This is precisely what the LSA type 3, the summary LSA, does. It represents the networks that are somewhere else, and where they are, well, behind my ABR that is connected to that area. And this would be the mental model of the network as area 0 sees it, of the whole domain. It knows itself perfectly, and as far as the faraway areas are concerned, I don't know nothing about the topology. I just see the networks that are present there. By the way, what would you believe would happen if I had multiple ABRs between area 0 and area 1? The question is, what would happen if I had multiple ABRs connecting area 1 and area 0 together? What would happen is that each of them, on its own, would advertise the prefixes in one area into another. And you would simply be looking at the total cost, because each of the ABRs may be closer to some networks and more far from some others. So you would use that one that appears to be the closest one. All right. What about area 1? Remember, area 1 sees things differently. What do they see? First of all, how many router LSAs? I'd say 4. The connections would be point-to-point because there are no shared segments here. And there is one network called network A in area 0 that area 1 doesn't see in detail but needs to know about so that they can route there. So there would be an LSA type 3, the summary LSA, injected by router 3 into area 1, representing some network in area 0. And that's all. This is what the area 1 would see. You're starting to get the hang of it. It's now getting a little repetitive, I know. That was actually the goal, because if it gets repetitive for you, it means you're starting to understand. Thank you. Now, I am intentionally skipping LSA type 4 for now, and I'm going directly to LSA type 5, which is AS external network. In simple terms, those are the prefixes you have redistributed into OSPF from somewhere else, a different protocol, or connected, or static. So let's modify the topology a little by adding some RIP domain above router 5. And there would be some networks, I, J, in the RIP, which you happen to be redistributing into OSPF on R5. And my question is, what happens in area 1? Now, all the process again. How many router LSAs? 4, because we have 4 routers, members of area 1. What their connections would be, they would look like this. By the way, you notice that I rearranged the diagram a little, but it doesn't matter where I put those nodes as long as those arrows go to proper devices. Of course, there would be information about a network in a different area, in this case, network A. But there would also be those 2 redistributed networks, I and J, that come into OSPF and that have been redistributed by R5. So R5 would be pointing to them. And this is how the area 1 would look like. I suppose pretty simple. But before I go to LSA number 4, I need to emphasize one thing I didn't mention so far. LSA type 1 and 2, router and network, they don't cross area boundaries at all. They simply don't leak. LSA type 3, the summary LSA, it gives you the feeling that it floods from one area to another. In reality, every ABR recomputes it and generates its own because it has to increase the cost. Right? So not even LSA type 3 is flooded across areas, it's just regenerated on area boundaries. LSA type 5, pardon, the external one is the only LSA that is flooded across area boundaries without any change. Nothing gets updated, absolutely nothing. Not the advertising router, nor the cost, nor the type, nor the prefix, nothing. And this creates problems. Let me show you, and again, there will be a slide and blah, 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 but what I want to show you is the problem that we get with the fact that we flood LSA 5, the external route, and not change it. The question here is, what is area 1 going to see here? So again, the tedious 3 routers, 1 common network between them, all the connections as they're supposed to be. The inter-area routes from the other area. And remember, we got the external routes flooded, but now we have a problem. They have been originated by R5, and that's written in their header. That's their originating router. But inside my area 0, there is no knowledge of R5. Where is it? Who is it? Which way? I don't know. So I cannot associate these external networks, these pieces of puzzle, with any existing stones of puzzle because I have nowhere to put them in. I don't know where. So this is the question that I have to solve, and this question gets solved precisely by the last type of LSA, which is the LSA type 4. It's also called summary LSA, but instead of describing networks, it describes autonomous system boundary routers in different areas. All that it says is, or all it contains, is the router ID of a faraway ASBR somewhere in another area. Because if I now know that it exists and that my own ABR can reach it, I know where to look for the external networks that are supposedly behind it. And this completes the whole set of LSAs as OSPF classically uses them. Routers, common networks, networks from other areas, boundary routers in other areas. Notice that Area 1 didn't need it. Area 1 had knowledge through LSA type 1 about the ASBR. And the external networks. Now for those who are familiar with also area types and maybe OSPF v3, a few closing remarks. First, those of you who know about type 7 LSA, or sometimes called the NSSA type of LSA, that one is in format identical to type 5, external routes. It's used in area types that want to distinguish between external routes in the backbone and behind it, which they don't want, and their own external areas they privately bring in and they want to keep. Because it would not be possible to tell apart my own external networks from the backbone's external networks. We simply advertise them in a different LSI type. But if you looked at it, format bit by bit is identical. So that's what the type 7 sometimes is used for, and it's for the so-called NSSA area types. If there are IPv6 aficionados here, they will point out that I may have not been entirely precise. And thank you, because truly I have not been. This information is about OSPF v2. OSPF v3, that was originally created for IPv6, it had to be because the old version simply wasn't able to do IPv6 stuff. They decided to split away the topology information and addressing information. This is something that ISIS, by the way, already does. And this allows avoiding recomputing the whole shortest path tree if all that changed is just an address, but links haven't moved, which is a perfect thing. So in OSPF v3 for IPv6, you only find information about who you connect to. Only the topology. Addressing is moved out into yet two another LSA types, the so-called link LSA, which only gets advertised to your immediate neighbor, and there it ends. It's not even flooded across a router. It contains the link local addresses and on-link addresses, and the true IP addresses on the loopbacks, on the interfaces, on the interconnections, are then carried in yet another LSA type, which is called the intra-area prefix LSA type. The basic idea, though, still holds for OSPF v2 and OSPF v3. Think of it as putting together pieces of puzzle, and if we created a separate piece of puzzle, it's because we want to describe a specific network type that needs special treatment. With this, thank you very much, and if there are any questions, I'll be available.